We'll present a little bit in Spanish and then in English.
Yeah, okay.
Bienvenidos a todos al último coloquio de este año, del 2024. No sé, sí, pero se engancha enseguida. Y tenemos hoy como oradora Ad, por favor corregime, please correct me if I'm not saying correctly, Ad Stoffelen.
Yes, very good.
He will be talking about wind, basically, but I will first review her career. He's dedicated to all aspects of satellite wind measurements, from new concept, from Calval wind retrieval optimization, operational production, to application and training in weather nowcasting. It involved data science, machine learning, MWP data simulation, climate data records, ocean forcing, marine water layer, and air sea interaction research. Now he's leading a group of active remote sensing from satellite using radar and LiDAR for ocean winds, clouds, and aerosols, and involves in the agency, the special agency Europe, AELIOS, Air Care, and Harmony missions are participating in the SAT and Union Europe Copernicus ground segment service. Thank you very much for being here, and the floor is yours.
Yes, thanks a lot for this introduction. So, yes, I will talk about observing Earth system dynamics from space. I added to it because we can do it very well from space, in fact, because of the spatial coverage of satellite instruments on the ocean surface. So you see some logos here. So some are from the Copernicus Marine Service, where we produce high-level winds on grids, level 3 and level 4. I will talk about them. You also see 3 logos from EUMETSAT. EUMETSAT has satellites that do wind measurement operationally for the meteorological community. So this is called the METOP satellites for the polar satellites where I'm working on. They also have a wind spectrometer on it, and I've been working all my career on wind spectrometers, so since 37 years. And also more recently, we worked on new data from space, which are from a Doppler wind LiDAR, and they measure actually in the upper air, they measure at the surface, but also measure tropospheric dynamics. And today we work on the recently launched mission, which is called EarthCare, my group, which also has a LiDAR, but not a wind LiDAR. It's only doing the optical, so it's looking at aerosols and clouds. I will say a little bit about that too. So yes, today in Europe in particular, we talk a lot about Earth system science. And of course, if you talk about Earth system science, you talk about coupling. So dynamical coupling between ocean and atmosphere is an important aspect of how climate will change. Very recently, we have had some publications about, for instance, the Atlantic meridional overturning circulation, that it could actually stop, which of course would have disastrous consequences for Europe in particular. I think also some here, because it would stop the heat flux to the Northern Hemisphere. The heat will stay in the Southern Hemisphere if this happens. We have a lot of data, but it's very difficult to predict these type of dynamical changes in the Earth system. Yeah, the more we measure and the more we can see with satellites, because it's very difficult to measure the Earth with in situ data. You have maybe 1 or 2 points, but the Earth is very big, so satellites are really very useful for monitoring the ocean and the atmosphere. And I have here a list of missions that cover the Earth, and the data sets are generally publicly available, so you can get them, you can work with them. And of course, that can teach you a lot about how the Earth is evolving and changing. Yeah, I was involved in these radar spectrometer missions, also involved in the AEOLIS mission. Now I'm also involved in some other missions I will talk about. Difficult aspects are, of course, the link of the satellite measurements to what happens in the ocean or the atmosphere, and how to compare that to models that look at these observables from a different perspective. We have to link them and understand what is the difference and how to work with them. Other aspects are the stability of the satellite instruments, how to calibrate them to make sure that they always give the same reading. And this is actually a main part of my work, and that's where I'm really experienced in. But also I have been working a lot with users my career, with nowcasting, oceanographers, and then you have to think about the geophysical processing. So how can you give the users what they want? So in our complex marine services, we started with winds, but now we do stress, we do stress curl and divergence. We can compute all these variables from the spatial data. If you look at it carefully, you can also calibrate them. And these data are available today for working with. And there's many applications in extremes, in waves, in surges, in weather forecasting, climate processes, climate monitoring, economy, energy, thermal protection. But there's many areas where winds are actually relevant, also in the coastal zones, of course, to do work. Then we have the questions of climate change. And we look at them mostly in terms of temperature and radiation, maybe atmospheric stability, thermal stability, humidity, clouds, and rain. But most interesting aspect is probably dynamical changes. So would the ocean change dynamically, like if the marinal overturning stops? It's a drastic change to the ocean. And that would have a much more impact effects than only the radiation change because of carbon in the atmosphere. But it can be triggered by this type of thing. So it's very important to understand dynamics. Also, the hurricane community is very interested to know whether hurricanes are changing because of climate change. And that is actually not a strange idea, because we have more humidity in the atmosphere. Tropical hurricane actually is powered by humidity convergence. If there's more humidity, because the temperature is higher and that can contain more humidity, it means that more energy will be converted in a hurricane, which could imply the hurricane gets deeper and stronger. So there are, let's say, quite straightforward reasonings why hurricanes could become stronger, in fact. And so it's very interesting to also look at these aspects. The ocean is also very important for the carbon exchange. The ocean takes a lot of the carbon that we emit, and that depends, of course, on the carbon content of the ocean and the mixing in the ocean and the atmospheric boundary layers. So also there we have to understand what the processes are doing. And of course, ocean heating also depends on not only on the thermal aspects, but also on the winds, because it's also fueled by evaporation, rain, and so atmospheric aspects coupling are also there very important. At the bottom, you see a depiction of convection, and the horizontal arrows are, in my view, actually very interesting, because what happens in moist convection is that you bring together moist air, you put it up into the higher atmosphere, and the rain drops on the surface and is therefore extracted from the atmosphere. What comes down is cold winds from the precipitation. They actually spread over the surface. So you are replacing moist, warm air with cold, dry air. And moist convection is a very fast process, so it typically has a life cycle of half an hour. So this is something that can happen very fast and continuously, and it has very big fluxes associated with it. But we do not well understand and resolve moist convection in global models. But we see them, for example, in spectrometers, and we can relate them to the moist convection process and study them. And of course, weather forecasting and climate change are very important, because the question I think most of you have in your mind is how much worse can it get? And when we saw last, particularly during El Nino, we see a lot of disasters every day almost in the news with gigantic consequences. So So El Nino is an aspect which is was very dominant in much of the weather in the world. So it's very strong differences whether we are in the El Nino or La Nina phase, particularly in the tropics and the subtropics. If you look at El Nino indices, they don't change a lot with climate change, in fact, but the weather changes a lot. And this is because in our changing climate, dry becomes drier and wet becomes wetter. So the extremes get more extremes, even if the index is the same. So we have increased evaporation and we have increased atmospheric water content. But another question is, can the dynamics of El Nino change too? So also could be the indices of El Nino change because we are changing the climate. And this is not a strange idea because also the mixing with the ocean and all the other aspects, they depend on, they determine the timescales of El Nino. If you change the timescales of El Nino, and maybe the cycle can also change. So the cycle is rather, it's not very, it's rather random, yes. So you don't need a lot of change to change El Nino cycling. But it's not known how this works. So the ocean is more than 70% of the Earth's surface. It captures carbon and heat, but also moderates the coupled dynamical response of system Earth to climate change. And that is, I think, also very important to understand. Weather models get better and better. So this is just a time sequence of the last decades, where you see the forecast scale of the European Center for Medium Range Weather Forecast. And the accuracy is relative as a percentage. So if the forecast is equal to the analysis, then they presume that there's 100% skill in the forecast. So this is how you go to 100%. And you see that in blue, there's the day three. Day three gets a lot better the last decades. And you also see two curves, a thick curve, which is the non-hemisphere scale, and a thinner curve, which is the southern hemisphere scale. And the difference is colored. And you see that the difference actually is disappearing. So the difference is close to zero. And this, one of the aspects why this is the case is that because since 2000, we use many satellites at the European Center for Medium Range Weather Forecasting, and they measure the same amount of data in the southern hemisphere as they do in the northern hemisphere. So therefore, you get a much better weather forecast here. And yeah, it's about the gain of 1 day per decade, and that gain is still continued. So we still are able to better forecast the weather. And that may still go on. We have now these machine learning models that seem also to be able to add some performance. So, but you will need measurements to initialize the atmosphere. So you cannot do that by machine learning. So that is a very safe area to work on observations. But models is these days a bit more complicated. But I also think that physical models will be needed to understand what's happening. So I think that's a big risk. So what we see is that we are better able to use the observations. We have bigger computers, and therefore we also have better weather models. So all these three things contribute to increasing skills. Then we can look at which instruments are used by ICMF, and we find that they are using more than 100 instruments to make a forecast. And in the way they develop this, every instrument has an impact on the forecast, which is beneficial. So they don't use satellite data if they're not exploited beneficially in the system. So that's quite impressive. And here you see them in a different way. They are stacked vertically as a function of time. And indeed, you see that around the year 2000, also in their operations, they start to assimilate more and more satellite data to these days. They're also used in reanalysis, so both in real time and offline. Satellites have large spatial coverage. They have polar satellites that go from pole to pole. So they give you essentially 2 measurements a day, one when the satellite is going up and then the satellite is coming down. We have continuous geo images, and we have geostationary satellites, different places around the tropics. So they also cover the whole Earth. And we internationally built geostationary and polar satellite constellations. So we work together with all the nations in the world to try to make a system that is useful. Yes, not that we all launch the satellites in the same orbit. It's much less useful if we spread them over time. That's what we're trying to do. We also try to intercalibrate as many variables you can measure with satellites: winds, waves, surges, sea surface temperature, ocean color, water quality, clouds, aerosol, rain, lightning, bathymetry, and so both ocean and atmosphere variables you can measure from satellites in principle. This is how the World Meteorological Organization is working with all different application areas to collect use requirements. And then, there's the satellite producers that also work together under the WMO to look at all these requirements and then define missions that actually can fulfill these requirements as good as possible. So they've published this in a 2040 vision, which you can find on this website. This is just a cloud sequence to give you some idea of dynamics. So what you see is if you can try to follow clouds particles, but you see that they actually are generated and they disappear. So it's not like that you can follow them because they are in a cycle of convection. That means that they last very short. But we can, of course, if you track the clouds, you get a very good impression of the dynamics, yes? Even if they are not good tracers. Thank you. Even if they're not good tracers of the wind, you can still try to track them and try to find out what is the relation to the wind and try to use it. So this has been done already since '68, so since a long time. And it's also used in weather forecasting. So these are examples of such winds in the atmosphere that are linked to clouds at different levels. But then we wanted also to measure winds in clear air, so in areas where there's no cloud. And in fact, it turns out that 75% of the troposphere has no cloud in terms of volume. So if you follow clouds, yes, you can see the flow, but only on particular levels where the clouds are, and not on other levels. If you look at the total content, where are the clouds? Then you see that on the right-hand side. Right-hand side are measurements of clouds with the Doppler wind lidar. The Doppler wind lidar has a laser beam, and it is scattered by the clouds and received at the satellite. And then we do the processing in a different channel than for the molecular winds, which is on the left-hand side. So we actually have to segregate clouds and particles and molecules in our processing because they have a different Doppler shift. And the Doppler shift is the way we measure the wind along the line of sight of the laser. So you see that in the left-hand side, you have many more data than on the right-hand side. So the right-hand side is what you can get from clouds and aerosol. The left is what you get from clear air. Aeolus has therefore been contributing a lot to get also winds in clear air. We took a long time to develop this satellite. It's very complicated to measure Doppler with a laser from space, and for molecular signal, you need ultraviolet laser, which is even more complicated than micrometer lasers. So, but we managed. The only thing is that when we launched it, it was a factor of 3 too low with respect to the design. Of course, this is a big disappointment because a factor of 3 is a lot. But when we started testing the data in data simulation, we found on the right-hand side, you can see that Aeolus has the second highest impact of any satellite instrument. So we lost this factor, but still, it's very important. And I have been the promoter of this mission in Europe. And of course, I explained to everyone why we should measure winds and why it is important and what impact we can expect. I compared it to radiosones and to other systems that already measure winds to explain to everybody what we can expect. And the impact is actually much bigger than even I expected. So although the signal is lower, the impact is the same as we expected. And that implies, in my view, that, and that's also what we see in the impact characteristics, that the models that we use for modeling the atmosphere are much worse than anyone thought. So if the winds are, of course, not as good as you thought, and you put in bad winds from observations, you can have beneficial impacts because you still improve it. This is actually what we have done. And this is also, of course, related to the flow characteristics, whether you can assume geostrophic flow or you have to measure geostrophic flow. If you want to have the flow on small scales, you cannot assume that it is geostrophic and in balance with the temperature field. So you cannot measure temperature to get the winds on small scales. Similar to the ocean, you cannot measure heights of the ocean surface to infer the current. You can do that, but you only get the large scale. Correct, you cannot do the small scales with this. The same is true with the atmosphere. This is the atmospheric experiment where we have shown that the flow characteristics actually of the models we have are not as good as we have thought before. And that's also one of the reasons why with machine learning you can actually improve it quite easily because yeah, it's not very good and it's easy to improve it. So still we can then look at the next Doppler wind lidar satellite, and we are now preparing it in Europe. Of course, we would like to predict how if we can reduce the errors by a factor of 3 or more even. We now think we can reduce the error by a factor of 8 in the next mission. What impact would it have? And this curve is just showing you impact in the vertical and error horizontal. So we have to do this extrapolation to better accuracy, which is not so easy. You see two curves here, a red curve and a green curve, that are different ways of predicting this improvement in accuracy. And also we did some experiments with observing system simulation experiments and ensemble data simulation experiments to try to find out how improved winds with the same sampling to improve the forecasts. And we find that doubling the forecast impact with a new instrument is probably not so difficult. But that's what we're going to try in Europe, probably around 2035. We may be able to launch it. But of course, first we need to have a design that is good enough. Then we have to convince everybody that they should pay. And then we have to build it, so that's why it still will take some time. Now, healthcare is a very nice mission because it also has a LiDAR and it measures also in the ultraviolet. And therefore, it can be compared to Aeolus in terms of the optical characteristics, but not in terms of the wind characteristics because it's not measuring the winds. But still, for the optics, we have now a second laser. And in fact, for Aeolus, for healthcare, we have 25% more signal designed. So that is very good news. And that's better than a factor of 3 less, of course. Not hearing anything. This mission is
video.
someone. I'm muted this. Should I sound up? I think it could be my laptop. I have to go out.
Sound of your computer or the sound? No.
Oh yeah. I don't know why it switched on the sound. Oh yeah, this is thing.
Yeah.
Okay. Not in my presentation. I'm not seeing my presentation on my screen.
We are.
Show why. I went out.
Maybe we can stop the sharing and do it again.
Yes, I can do that.
Because we are seeing the.
Yeah, you still see it, huh? The screen. Okay, so now I share it.
The bottom.
Yes, okay, we're back to where I was. So let's continue. Yes, and why would we need a laser to get clouds? This is because, as I showed, the atmosphere is very dynamic. And if you look at features, they can actually change height while they are moving. It's very difficult to, from the image, assess the height of the clouds. You see that in these plots. So here you see the plot from the height that is inferred from the stereo technique. I will go to that in a minute. And a laser technique. Then you see that the heights are very close to the diagonal, so they infer the same height. But if you compare the laser with an optical instrument in terms of cloud height, then you see that the cloud height is very dispersed. And that also is true when you compare the stereo clouds to clouds from the geostationary satellite. You also get a very broad range of clouds. Cloud height is very important because the average shear in the atmosphere is about 4 meters per second per kilometer. So if you are wrong by 1 kilometer, you make an error of 4 meters per second. So you need to get the height very good to get the winds right. And that's what we did with Aeolus. But also you can do that with stereo. Stereo means that you look at the same cloud from different directions. Then you will see the cloud seemingly in a different place on the Earth. Because you look at a different angle. And then from the difference, the parallax, it's called, of the Earth, you can compute the height of the cloud, if you know the geometry of your measurements. And if you do that then a few times, then you could actually see the cloud move, of course. So you could also do winds from this technique. But if you do it in time on a satellite, then the satellite will also move. The cloud will deform. So you have several problems at the same time. The cloud is actually deforming at a speed that is visible. So you only take about 10 minutes to pass a cloud, the satellite. But in this 10 minutes, the cloud changes so much that getting accurate winds is already difficult. So that's how fast clouds change. So then in the new mission called Harmony, we actually have tandem satellites. So they can look at the same cloud from 2 aspects in space and try to work out the height. And then also repeat this in time. And then we don't have this problem that we have entangled motion and position information. And we probably can even measure the change of the cloud in time also with these 2 satellites. So it's at clouds. So that's what we're trying to do. This is an example of a stereo cloud system that's existing from 1 satellite. It's MISR. And here they plotted the wind component that is resolvable from the instrument from 1 satellite. And if you want also to resolve the other component, you would need 2 satellites. So this is just a preview of what you can do with 1 satellite. And this is the top of a tropical cyclone. So here you see that the cloud tops hit the ceiling of the cyclone and spread. You can see that in the winds that are computed. So this is quite convincing. Now go back to the ocean. So we have a lot of processes at the air-sea interface. Exchanges of heat, gas, and momentum at the air-sea interface depend on thermal, chemical, kinematic imbalance between the ocean and the atmosphere. They're modulated by many small-scale processes that substantially moderate the exchanges. You see a lot of different processes here, and I will not go into all of them because it takes a lot of time. But there's of course wind wave current interactions. There's all kinds of flux anomalies. There's organization in the air, so eddies in the air, boundary layer wells. You have also organization in the ocean, of course. You also have an ocean boundary layer that's organized. In general, organization leads to more efficient exchanges so the RC fluxes do depend on the surface stress, boundary layer thickness, because of mixing, and also kilometer scale ocean dynamical circulations and phenomena. The atmosphere and the ocean are dynamically coupled through all these processes with parameterization errors. And yeah, I will show some problems with winds later on in models, but the problems can be really big compared to the random errors we measure with satellites. And they're also biased, so they're systematic errors. And that implies that these systematic errors can, of course, also change the mean in principle. So it's important to know what is happening. And they certainly change the dynamical processes. The oceans are more than 70% of the Earth's surface, so understanding coupling between the ocean and the atmosphere is very important for climate dynamics. Tropical modes are particularly poorly described, like the El Nino already mentioned, but also Mediterranean oscillation of tropical instability waves. And we don't actually know quite well how these behave. The question is, will these modes change in the changing climate, and what are the consequences of these changes? There was a very nice article in the New York Times a few years ago about the ocean ice dynamics. It's very accessible, and I put a link here so you can have the presentation, so at your leisure to this. But it is about also how about a link between atmosphere, ocean, and sea ice. And of course, yeah, if you change things at the ocean surface, may push water one direction. It implies that water will also flow differently at lower depths to have circulation. It can change the mixing. So this article in the newspaper is about this. And so it's about the three-dimensional circulation, transport, mixing, about heat and carbon budgets, how it could be associated with melting sea ice, and accelerating the land ice on Antarctica also. And that's of course also associated to sea level rise, which is of course crucial for climate change impact and understanding. Satellite capabilities are limited to the surface, but we already have a very big, we have substantial Argo floats in the southern hemisphere to get a better picture of it. So we do a lot of wind processing at KNMI at all levels of processing. We distribute them in near real time and also as climate data records. We distribute them all over the world. There's of course many organizations involved in this, both the producing organizations and as user organizations, and we have contacts with them. We have a help desk support if you are interested. We are now growing a virtual constellation internationally, and there's many uses of this, but one of them is extremes. So this is the landfall of one particular hurricane. And you can see that we have 5 acquisitions, ice spectrometers of this hurricane during the landfall. So the constellation is of course very useful to monitor tropical hurricanes and to better give warnings on where you have to mobilize people, warn them about the effects of the hurricane or strength. And there's a story about this. And you can also learn scientifically from these type of events. Then we have also developed coastal winds. So this is an example of an area where we have produced coastal winds with different flags, and we validate them against the buoys that we have. And so we can produce very accurate wind vectors very close to the coast. Then we also have these higher level ocean surfaces. So Spectrometers or satellites typically measure in swaths, the Earth's surface, that's the area they sense. And then for the satellites, these areas have also are elongated across the poles, so they are strips. And we process all these strips in our level 2 processing, but many users, they would like level 3 data or level 4 data. So we then also put Earth-gridded data. We process them in level 3, and then we also have collections of data in level 4. So we now have, for example, an hourly level 4 product, which is replacing Area 5 as total surface wind. So, and it's correcting the biases in Area 5. So Area 5 has a lot of local biases, which you can see here. So you see on the top the difference between the spectrometer and Area 5 or operations, because it's very similar. And difference is here in meters per second, and it covers a month. So for a whole month, near the equator, you see a difference of 1.2 meters per second. Also here close to Argentina, you see, for example, that there's low bias, about 0.5 meter per second over the whole month. Because if you force the ocean with these winds, you of course have the wrong forcing. So these biases are very important. On the bottom, you see what we call transient wind speed difference between the spectrometer and, in this case, ASCAT-A, collocated with Area 5 of 2018. Transient means that you can look at the means, look at the difference in the means, but then you can also look at the standard deviation, look at the difference in the standard deviation. So the bottom plot implies that the variation in winds by a spectrometer, measured by a spectrometer, is much higher than the variation in winds measured by models at the same points, because we sample it at spectrometer points. That implies that the variability of ocean forcing in the model is too low. And variability also has an effect on ocean forcing, not only the mean. So it is also quite relevant. Yeah, so we also have products that are derivatives. So we also have wind stress curl, differences between model and spectrometer, divergence, differences between model and spectrometer. So you could in principle test what is the effect of changing the forcing onto the error, and is it important or not. So that is why we have produced everything with respect to Area 5 and everything with respect to the ECF model. But every user can test for himself how important is it to take one or the other. Yes. There's other ways to measure winds at the surface. This is GNSS-R. So there's the Cygnus mission, I think is the most well known. It's launched by NASA, and it was measured. It was proposed as a hurricane mission. It's not such a good idea because GNSS-R is not sensitive to extremes, in fact. So it's more sensitive to moderate and low winds. It's because it's bistatic. And bistatic implies that if the scattering at the surface is increasing, you receive less signal at the receiver. Because the more the wind increases, the more rough the ocean gets and the less radiation is going back to the other satellite. It gives lines of responses, so that's very good to fill gaps between spectrometer data. So there it's very good for. It still flies, so it is interesting. Then for processes, we have this Harmony mission. I already explored that we have a stereo infrared camera system, 2 satellites, that will be part of this Harmony mission. And the Harmony mission is also a radar mission because it's 2 satellites fly around the Sentinel-1 satellite. And the Sentinel-1 satellite is a SAR. Also measures wind, but only for one aspect. And now with these 2 other satellites, we get can receive the signals emitted by Sentinel-1 in two other aspects. So then we get the ocean surface from three different aspects, which is looking like a scattorometer. So we can actually get also direction. We get vectors. So we're trying to measure ocean current vectors. We're trying to measure ocean wind vectors. And we're trying to measure waves at a resolution of about 1 kilometer. Sentinel-1 is not global, and Harmony therefore will also not be global because we depend on the emitter of Sentinel-1. So it's for our sample. For example, it's following hurricanes. It is doing a lot of ice scattering, and we have still some space to ask for more data in the Sentinel system to profit the Harmony mission. So we will be working with this. So then to finalize this talk on Earth dynamics from space, winds determine hurricanes, weather, waves, surges, electricity, ocean forcing, heat and carbon budget, sea ice decline, climate change. So there's many different applications of winds, particularly of surface winds. They are used by marine forecasters in numeric weather prediction, by oceanographers, wind engineers, offshore industry, safety authorities, climate scientists. So we have a lot of contacts with all these different groups. We have more becoming available through international exchange. So this is the so-called coordination group of meteorological satellites. They have virtual constellations, and there's also an ocean vector wind virtual constellation, and this is part of it. We see ongoing technical development of capability. We see that data science is prominent, and advanced statistical physics-informed methods have been developed for instrument monitoring, retrieval, and applications. We can well use new satellites, but certainly more resources for improved exploitation of existing satellites in society. So I'm working on retrieval, but working with the users for them to use the data is challenging because you need new resources if you put in new data. So that is the problem. Maybe sometimes you can reduce your old resources, but most of the time to first increase and then maybe reduce or something like that. So it's always difficult. Also, ICT facilities are problems for several users, although we try to offer the data as easy as possible. These things are improving a little bit because there's more and more open surfaces and computer clouds that allow collaboration. Therefore, also further progress because you could use these clouds to work on the same data and work on sensitivity tests as a group. And that will allow that you make faster progress. So to make progress, we need to, of course, we have to share the Earth because that's where we all on. There's no choice. But also we can share the satellites, the science, and the services. Thank you. There are some references in the end, if you both scientific and services that you can look up if you're interested.
Thank you for your talk. It's really interesting. And now we have a space for questions for Zoom audience and also here the one we are in the present version. Also YouTube. On YouTube also. I have I think mainly two questions. For sure, maybe I have another one. You show us a lot of products, and one of my first question is maybe because I am not a meteorologist. I was thinking about the one with the laser that you can measure the width or
the width,
the cloud.
Yeah.
You can measure how high, how deep.
Yeah.
Of the cloud. I was thinking about, because you said that also when you have a two laser or well a tandem mission that can measure the clouds when they are moving, you can derive then the wind. But that process, that methodology of should include the at what level of the atmosphere you are because I know for the few things that I know is that depending on which kind of cloud you will be more close to the surface or up high.
Yes, yes. So that goes back to this slide. So about parallax. So as the parallax increases, the cloud height increases. If you know the geometry of your satellite, and you make an image and you look at the location of the cloud on the Earth, and you have to, of course, to verify it's the same cloud. Yes, that's the most difficult part. If you don't know it's the same cloud and you know the distance, you know the height.
Right. Geometry. Okay.
Yes, that's geometry. Then if you can do this measurement as the satellite is passing, you could in principle also compute the movement of the cloud.
And then my other question was about the wind product that you said that you have L2, L3, and L4, and I was wondering because I didn't check yet if you have the as level 4, the one that merge more than one wind mission, or there are only, for example, like before.
Yeah, tomorrow I will talk about this effect. We have many spectrometers now. So we process today 24/7, 7 spectrometers, 7 points. And then it implies that we can also so this is the list of wind spectrometers that we process. Some of them have LST, which means they have local solar time. They are sun synchronous, so they always pass over at the same time of day every day. So you do not get any collocation almost between 930 LST satellite and the 12 LST satellites, because they just are at they're different times. Yes, so they never meet. But then there's also a few satellites that are regressing. And that implies that the time of day that they pass over will change. It will change gradually over a month, but that implies also that they will collocate with every other satellite in spectrometer that's flying. But now we can collocate them at exactly the same time. They measure the wind. And then we can look at the differences and try to find whether the differences depend on the geometry of the measurement or so against all different parameters that we can. That are varied in the satellite system. And then also the geophysical model function, the quality control, so we can compare these things and then improve correspondence between the satellites. So this is what we have done in the last years. And you can see here OSCAT2 and ASCAT, they are actually quite close in time, 8:45 and 9:30. So they have many collocations. But they are very different spectrometers. One is C-band, it's 5 centimeter wavelength. The other one is 2 centimeter wavelength. The HCAT has 3 static fan beams, satellite, and the OceanSat-2 has a rotating pencil beam, so parabolic antenna rotating. But they're totally different satellites, wavelengths, geometry. But we are still able to match them, so to get the same wind at the surface from these 2 very different satellites, and also to get then the same biases against the ECF model. So it also gives us more confidence that the ECF model is wrong, not the satellites. So we are able to bring this closer and closer together because we have more and more satellites. It's a lot of work, but it's really productive. So if you have the data, it's something you can easily try to do. And I think your question was about whether we combine products, yes?
Yes.
So now we had a PhD student, and she actually combined all the different satellites to compute level 4 products, and that gave the best level 4 product for that setting. Because you have so good sampling, you can already produce the model bias after 5 days. If we use only one satellite, we can only produce a good model bias after 20 days. And that means the ocean can change, of course, in 20 days. that we then miss this change and we average it out. But still, also with one satellite, it works quite well. It's not much difference. But we will try to progress to put everything together. That's the idea.
Pedro has. You can ask.
Yes. Thanks for the presentation. I was wondering while I was listening, if you can comment on how what is your opinion? What do you think on these products to apply for in regions like in the southern hemisphere, like in Patagonia or even over the oceans, in which we have these relative strong winds and low surface observation. So can you comment on what if that is you see that as a problem, or what is your opinion on applying these products on these regions?
Yeah, so this plot is actually of interest, maybe.
This one is very impressive.
Yeah, so what you see is that the southern hemisphere scale and northern hemisphere scale come together if you apply satellite data. So it implies that the in situ measurement system, as you say, is rather insufficient in the southern hemisphere because a lot of it is ocean, and it's very difficult to make in situ measurements of the atmosphere, but also of the ocean in the southern hemisphere. But now, if you have satellites have the same spatial coverage in the northern hemisphere and the southern hemisphere. In particular, the wind spectrometers that I'm working on, they have more impact in the southern hemisphere in numerical weather prediction than in the northern hemisphere. This is because there is more water in the southern hemisphere where we can measure. So that's why we, of course, improve the weather forecasts. And as the other aspect is that the winds we get now these days are also more accurate than the winds you can get from a model. So if we have many spectrometers, then you can actually take even more benefit of winds if you are interested in surface forcing aspects.
So it will be reasonable to use these products on the southern hemisphere.
Yes, they will have. It's I would say it is it's easier to apply them in the southern hemisphere than in the northern hemisphere. In fact, you know, I'm from the Netherlands, so we are 2/3 below sea level. So we are very interested also in the winds in the North Sea and the Atlantic with spectrometers. So that's why we do this in the Netherlands. And we also have some Caribbean duties where we are interested in hurricanes. So that means that for us it's very nice to do this work and help improve weather forecasts in those areas. But certainly here, it's I think even more obvious to use these data.
Okay, and the performance of these products is not related to the energy of the winds. It's you would say that is that is not like regions in which you have this strong winds or these westerlies against other regions with other predominating other processes like convection or things like that. Do you think the product has maybe the question is if it has a spatial heterogeneity of the performance, no, even within, you think?
Yeah, so we looked at that very extensively in the past. So we specifically looked at moist convection in the tropics, and we then do a method called triple collocation. So we collocate buoys with spectrometers with models, and then we look and we have some we can also measure the wind variability with spectrometers. So we can actually make these accuracy assessments as a function of the wind variability that the spectrometer is seeing. So if we have high wind variability in the tropical region, then we see that the model errors go very high. So we have like 5 meters per second ECF model error if the wind variability in the tropics is high. But the spectrometer error is not increasing. It's only increasing a very little bit. And then because the wind variability is changing. So then we did comparisons with buoys, and we integrate the buoy wind over the time that is equivalent to the size of the footprint of the spectrometer. And if you do that, the buoy and the spectrometer get closer. So then the winds stay with accuracies that are below 2 meters per second, even for very dynamic conditions. And also we use ASCAT now as for hurricane forecasting. So we found out while applying ASCAT for hurricane forecasting that actually the most accurate winds you can get in a hurricane are from ASCAT. So we tried to verify them with the hurricane hunters. I've been flying with hurricane hunters myself because they were interested in calibrating the European spectrometer. And I've been working with them now for 20 years. And in these 20 years, first we used their SFMR instrument on the plane as a reference. And now after 20 years and also more than 50 years of ASCAT, we find out with ASCAT that their airplane instruments are not very stable. So the satellite instrument is stabler than the airplane instruments. And now they even decided not to give the airplane data anymore to the nowcasters because they don't trust them anymore. And this is because with satellites, we have proven that the quality of their measurements is changing in time. So I would, every time we look at something new, we find that the satellite is doing a very good job. That what we try to use as reference is difficult. And goes back to the community. We also found out that the tow buoys are now biased by 10% because NOAA put in new system in their so they replaced the anemometers of the buoys. And we found out with the satellite data that they are changed by 10% in the wind speed, which is a lot. But you find it because against satellite references, which are stable, you see the change.
I have a question because you speak a lot about climate change, but I don't understand if this product is for predict something in the next days, in the next month, or in the next years. I don't understand. If you want to study climate change, it's a process of large scale time. So
yes.
These kind of products are useful for studying climate change in the next, next years, or just to forecast what is happening in the next hurricane and some phenomenon that is coming in the next days.
Yes. So currently we use satellite data, because the winds that we measure are independent from other references, yes? They are very stable in time. We have methods to physically calibrate spectrometers to accuracies below 1%. But that's something we can do. Just because the physical signature of a spectrometer is not changing over time, so we can always calibrate to it and find the calibration of the instrument. It's very stable. If you use RF5, it's not so stable. And why? Because the model is stable, but the observations that go into it, they change as a function of time. I showed you what ECF is using as a function of time. This is also what goes into RF5. And they use artificial correlations between, or empirical maybe, between upper air observations and the surface. So we do see that the surface is changing if they put in more microwave radiometer data. Not as much as in the past, but still it changes. So what we already have done is to monitor the wind change in the model and compare it to the wind change that we see with spectrometers. Then we sample them. We sample the model the same way as we sample the spectrometer, as the spectrometer is sampling. So we look at the differences for a given weather sample. And then you see that the changes are different in area 5 and the spectrometer. We're now doing a study where we're going to look at tropical hurricanes. So, as I said, we spent quite some time now on extremes. So with a spectrometer, you can measure whether tropical cyclones are becoming stronger over time. There's no other method you can do this with. And so it's about the past, because we are using observations. So if we know what these observations are, we can see how things change over time up to today. And then see, yes, these plots. So these plots are showing errors in the mean of reanalysis and errors in the variability reanalysis. And they represent the dynamical aspects of the coupled system between the atmosphere and the ocean. If you do this wrong, then of course you have the dynamics in your system wrong. And if we can show that these biases are changing over time in area 5 from 1990 to today, then it implies that the observations that are used in area 5 have different constraints on the dynamics in 1990 than they have today in 2025. And that is important to know, because if you infer climate change from area 5, you actually assume that it's all staying the same. It may not.
This bring you any trouble with the climate change community?
Yes,
Because,
it did, in fact. So on
that would be very low.
this, there's maybe a story, a short story. And we had a sea ice minimum in the northern hemisphere, which was in 2012, I believe. And because with the spectrometer, we also measured the sea ice extent. So Dutch media came to me to ask about sea ice extent. So I looked at sea ice extent, the records that we have, and plot them over time and make a regression, the first thing you do. And I saw that sea ice was going down much faster than IPCC was telling us at that time. And then, but I had to go to the TV and the radio to talk about this. And they were all interested. When can we row to the North Pole? That was the first question, of course, the journalist is asking us. And I said, so I knew I had to solve this problem before I was going to talk to them, because I was not going to say that ice would only disappear in 2100, because I knew it was not correct. It was not consistent with the observations we have from satellites. So why would I tell a lie because there exists an IPCC? Yes, that is a bit. So my scientific integrity said I have to solve this. So I went to the modeling people at KNMI, and I gave them this story, and they said the first response was, no, you cannot deviate from the IPCC, because the media already criticized IPCC, and this will be another problem. And then I gave them my simple calculation and the data, and I said, well, what's wrong in my calculation, and can you tell me why this process would slow down? Because I could think of mechanisms to make it faster, I could not think of any mechanism to make it slower. So then they looked at it and they gave me back what the models predicted over the last 30 years and for the next 100 years. This was a paper, and I looked into the paper, and these models were everywhere. They were not even close to the last 30 years of observations. So he said, yeah, you give this to me, but it's based on no observation. So why would you believe this and not my record that is based on satellite data? And then we had one scientist, and he also got a bit into, he wanted to solve this. So he took only the models that compared to some extent with the observations over the last 30 years, and then looked at the projections of these models. And of course, these models, they coincided with the regression line. So then they said, okay, you can go on TV and tell them that the sea ice extent may go to 0 at the North Pole somewhere between 2030 and 2060, rather than 2100. Yes, so you of course, as a scientist, you want to test your statements against observations. Yes, that is the basic premise. You're not going to say something that's only based on artificial models. So this was, I think, a nice example of how this can bring to a real conflict. Yes, that's a good question.
One question here for curiosity. If you're interested, or I was wondering, you also consider comparing what you measure for wind against the consequences of wind that you can also measure with the satellites, such as dust, for instance, or I think because I study phytoplankton blooms in upwelling regions. So
yeah.
I don't know if that is something that you also push for or are interested in.
Yes, I'm in the Copernicus Marine Service for these higher level wind products. And of course, one application is to test them with ocean models. And I push for this. And what they tell me is that in these operational models, they have other problems they want to solve first, particularly on the global scale, before they want to improve the wind forcing, because I think other problems are more severe than the problem of the wind forcing. But if you look in a bay, you're interested in phytoplankton, sediment transports, then of course you use a local model. I think in that case you are actually interested in the local forcing conditions too, because the winds that you get from a model, they may be systematically wrong by a second, meter per second. And if this persists over a long time, maybe it's more emphasized in the particular conditions where you have mixing, then it can make a difference. We have seen some examples of this also in the Copernicus Marine Service in the Bay of Biscay, where they looked at certain conditions at some buoys, which they could not explain with the model. And, but they used perturbations around the mean state, which was off by more than half a meter per second. So then, if they would change the mean forcing by this amount, they actually could explain the difference. Because if these differences are very persistent, like they are, then of course it can make a difference in the analysis.
Thanks.
Last one question. Maybe two. I will ask the last one, quick one, related with regional coastal winds. You mentioned that you have coastal product, and I would like to know if that product is for all the coastal region or for now is only for an area.
So for HCAT, we implemented a coastal wind product for the whole globe.
Okay.
Yeah. But we are also still working on it. So in the coastal area, the problems that we can occur are with infrastructure. So, for instance, particularly in the Netherlands, we have the Rotterdam Harbor. This in the sea, not in land, but in the sea. And there are these, always more than 100 of these massive container ships lying around in the sea. And they have so-called containers are called reflectors for the microwave, so they scatter radiation back to the satellite. And then our quality control sees that and throws some winds out if the contamination is too bad. That complicates things a lot because change your climate data record if you wish, yes. Particularly with low winds, winds are not acceptable. High winds, they are more acceptable. By doing then this data quality control, you throw away a lot of low winds, but you don't throw away the high winds. You should make a mean plot of the wind. Get much higher winds afterwards. So then so therefore we do also collocation with the model. Then we can sort of estimate the effect of the sampling. We have to do a lot more work then to make it make corrections for climatological use. Yeah.
Well, thank you again for your talk.
Thank you.
See you next year.
That's